I don't think it's good to call them reaction diffusion, but it's the same kind of spirit where you have the reaction would be the cellular dynamics in a single cell, and by the hardwiring hypothesis, this is going to be the same dynamics for every cell. And so if they're all not connected, they're all going their own way, but now you take into account the diffusion term, and that's going to amount to adding in the Laplacian to this separate dynamics, one for each cell. So you have the Laplacian term which connects the cells, and the reaction term which works in cell by cell. So you get the combination of the diffusion together with the cellular dynamics. So that's the kind of model that we work on to obtain, for example, this idea of getting this cohesive picture, because we want to see when does this lead to dynamics which is going to be the same for all the cells, and even this, not only the same dynamics in each cell, which we almost have by hypothesis, but we want to have the beating in unison so that the initial conditions are smoothed out by the Laplacian diffusion terms. So it's not, these are ideas that are in some form or other are pretty common, especially because of the PDE reaction diffusion equations. But we exploit that seriously. Okay, but then I haven't mentioned maybe the main recent scientist who works on these things is Kuramoto, Japanese scientist. And what Kuramoto does is something different, but very closely related. He works with angles. He works with the angles along a periodic solution, or points on a periodic solution which can be given by an angle if it's a closed solution. So Kuramoto is, I think, the biggest name in this subject, being in unison in the last 20 years or so. But he starts with the dynamics of the angles. And of course that's a lot simpler than what I've been saying, because if you look at the proteins, especially when you take into account many proteins, then it gets kind of complicated because you have a different Laplacian for each protein, and they're all kind of organizing all at once. But in the picture of Kuramoto, you just have the angle. That still would be an angle for each protein, and you get the synchrony for each protein. But that's Kuramoto. And so what we did then was to look at, we've been looking at this picture of Kuramoto for us. And we have the same phenomenon. If you understand the Laplacian situation, you can also understand Kuramoto's picture too, because there's the same effect. There is a tendency to average out the thetas, even as far as the initial conditions. Just like with the Laplacian, you average out the initial conditions through the diffusion. And so you have this phenomenon going on in Kuramoto, but it's all done with angles. So one can connect up the two. See, they both have their advantages. But if you look at this hard-wiring hypothesis, then you're going to focus on a single periodic solution which is stable. Initially, it will, without diffusion, each cell is going to be going around with different initial conditions around this periodic solution. That's going to be an abstract heartbeat. But you want to synchronize the initial conditions, so that's where the diffusion comes in, and so that's the model that we pursued eventually. And this, with Kuramoto and this picture, which we have now derived from the Laplacian picture, he does get meeting in unison to a great extent. But he gets it in a crude sort of way. He will get something about the dynamics starting with almost any initial points will lead to this being in unison. So they will achieve synchrony for almost any initial point. So what we've done is, well, we knew this from our own point of view too, but we also want to get much more than that. We want to get the structure of the dynamics. So this structure of the dynamics goes way beyond just the questions of being in unison. So that's what we've been getting on. And when I speak about some of these things, I'm not necessarily having the support of my two co-authors. Yeah, we have lots of conflict. But what I like to pursue is a picture which gives the dynamics very precisely and simply. And then I believe it can be proved, but I haven't given all the details, prove that is the actual dynamics. And the idea is going to connect up with Morse theory in this picture I have. So Morse theory, I don't know if many of you know, Morse theory counts the critical points of functions on a space in terms of the topology of the space, Betty numbers. So the way I've been pursuing this is to take Morse theory of a potential on the torus. So here's the main idea. So we have a potential V on the torus. We have M cells. Then we have a potential like this. And we have suggested a potential function such that minus gradient of V is equal to the Kuramoto equations. So Kuramoto then is described exactly as the negative gradient of a potential function, of a function. So V is just a function which we describe. Partly our description is motivated to get this equation. This minus gradient is the Kuramoto equations. And that, I think we all agree about that. That's fine. And now I want to describe this dynamics. V is obvious. It's pretty obvious what we should choose for V. V is simply the product of theta with sine squared theta I minus theta j. This should be sum. This is V. Sum of the differences, sine squares of the differences. Then there's a 2 in there. But you can figure out what the V should be by this equation. Minus gradient V is the same as the Kuramoto equations, which is a huge literature on. Kuramoto equations are a big deal. So this puts the Kuramoto equations in our setting. And now, what is this dynamics going to look like? And the idea, so if you understand this very well, then we'll get the Kuramoto equation solutions, and we get the whole dynamical picture. So this is a way of getting a precise picture of the dynamics for the heartbeat. So we can get it this way, almost an exact picture of the dynamics. It's given, in fact, by what's called a perfect Morse function, perfect Morse theory. Once one has V, then there's the simplest dynamics that will give rise to what we want. That's the conjecture we make. This is all on the torus, the M torus, when there are M cells in the heart, M myocytes. Okay, So, and here's what I like especially, is the idea of understanding this is to take antipodal pairs. So you can think of this being the circle, and here's the theta point here. So we look at pairs of thetas, standardized pairs of the, let's take n even. I don't know how to do it for m odd. So if we have an even number of cells, that's the same n as in the torus, then we take theta 1, theta 2, and so on, joining antipodal points. And now we do this with all of them. So every point is the torus is represented in this way as one of antipodal pairs. Now this has got some nice properties. As you rotate this, it doesn't change V. So V is a variant on the rotation of an antipodal pair. So these antipodal pairs are set up to give us a complete way of getting a complete picture of the dynamics. And then the critical points, the Morse critical points, will be given in terms of these pairs. So this would be 0, this could be pi. And we do this for m over 2 pairs. And now we get the critical points of Morse in terms of how these are written. Some of them will have, some of these pairs may be degenerate, so you get the index of Morse in terms of, you know, how many pi's there are. So in any case, this gives, you know, a very clean, nice picture of the dynamics, and it's the best dynamics consistent with Morse theory. And it doesn't prove it that this is the only picture, but what one can do is do things like move this around. This pair can be twisted around so that all of these pairs become the 1 pi, because it leaves invariant all the dynamics, chromodynamics, and everything is invariant on the rotation of an antipodal pair. So that allows one to get a bunch of antipodal pairs. And from that, one can get the whole dynamic picture completely. Anyway, that gives a little bit of the subject as I see it. Thanks very much.
Thank you, Steve, for a very interesting talk. Any questions?
First question is, because you're talking about hard wiring, so that concept mathematically, how you really describe it, does it mean some kind of set of ODEs, and is ODE some kind of periodic solutions, and they sort of different from each other slightly or something like this?
The hard wiring would mean that each cell in the heart, each myocyte, the ones that are responsible for the heartbeat, each of them has a basic periodic solution, contracting on periodic solution with exactly the same dynamical system for each one. That's what hard wiring will mean.
Yeah, but in the mathematical term, I mean, when you finally formulate mathematical theory,
Yeah.
so that means they are the same ODE?
Yeah,
The same ODE.
Same, different initial conditions.
Yeah, I mean, different initial conditions, the same ODE,
Yeah.
and uncoupled, same set of ODEs.
Right.
Represent each individual cell.
Absolutely. And the coupling will come from the diffusion.
From the diffusion of a discrete version of the Laplace.
Yeah. Right, exactly.
So another question is about the diffusion, and when you treat the diffusion, you sort of couple these ODE systems, right? So you put the ODE together now with some kind of coupling.
Yeah.
And the coupling represents some kind of diffusion, right?
Right.
But how do you exactly put them together? I mean,
Add them.
just add them together.
Yeah. You add them. Yeah. I'm oversimplifying some things. I mean, after you add them, then you want to separate them. So you could say the dynamics is really the diffusion plus a term which corresponds to a translation. And the translation is there because you've compressed things to a single periodic solution, and that if you forget the initial condition, you're just moving around that periodic solution. Then you're getting close to that, so the approximation is that it can be dealt with mathematically.
Okay, one last question is, when you talk about the diffusion, is it locally? I mean, is it only for the nearest neighborhood? So the connection is only related to the neighborhood, right? I mean, it's the cell here, then maybe about a few, finite number of cells around it, right?
It's global.
This is global.
Assumption, my hypothesis. See, I'm assuming, that the dynamics of each cell is globally
Connected with other cells.
no, it's globally, in its own right, is the same periodic solution with the same dynamics as each other cell before diffusion.
Yeah, but I'm asking the diffusion part.
Oh, the diffusion
is only
connection.
locally connected, right?
Oh, no, but globally, it's the Laplacian that works globally.
Yeah, it's globally, but the Laplacian is sort of locally connected, like discrete Laplacian or something, so you only connect with maybe 4 neighborhoods.
Yeah, no, it doesn't have to be, I mean, it works, you can generalize the Laplacian quite a bit, but, normally you'd think of it, interpret it as the membranes between 2 cells, and that would give rise to the diffusion. And everything is so oversimplified. People ask me, what are you doing realistic? And say, no, I don't like realistic mathematics. I mean, my example is Newton in Principia. All his beautiful mathematics, except for the heavenly mathematics, all of it is too unrealistic, because there's no friction in it. And it took 100 years after Newton to put the friction in. So he idealized drastically, and it was a good idea. So I'm inspired by that to idealize, not make it realistic models.
Thank you.
Thank you very much for the presentation. I have 2 questions for you. The first question is, I understand that these mathematical model units is working for testing fault.
Yeah,
And we also understand that when the cell is not synchronized, may cause fibrillation, arterial fibrillation, mitral fibrillation. So engineer give a shock, we call it defibrillation, can save people's life. So my first question is that how to modify this kind of model to applicable to desynchronized heart. How do we do the kind of prediction, if possible, transition from heart to desynchronization, so that we can have early intervention or treatment, so that people will not die from desynchronization.
yeah, so I'm doing things to understanding, not, in a kind of immediately applied way, but I think understanding of, for example, these models that we're talking about could be useful to see how they break down when it comes to understanding arrhythmias in the heart. So I'm assuming a lot of rhythm here in the heart. But if you want to understand some aspects of disease like arrhythmias, then you can use these models, I think, to understand that. I don't know if that helps.
Yeah, thank you. My second question is a little bit bigger pictures. I like what you say, your cell beating unison when you generate a heartbeat, very clean ECG.
Yeah.
So that's my first time to hear, mathematician, famous mathematician talk about the heart. I never had this kind of opportunity before. So I attended many other talks by medical doctor, physiologists, particular engineers. But every group of people talking about is heart. using different languages.
Mhm.
If you think about probably you know better than me, globally, the heart problem is still number one killer. 17 million people die from these diseases, huge proportion, almost double of the deaths of the cancer.
Mhm.
Bigger question is that, can you suggest a way that the people who work in a different field together in a unison manner, we eating together, fight with disease prevention? What's your idea? What's your suggestion?
Oh, I don't have too many recommendations what other people should do. You know, I just try to work the other way around. If I can inspire some people thinking about these questions, then I'm happy. So I work from the point of view just hoping to inspire somebody about maybe a little different way of thinking, like what I spoke about today.
Thank you.
You think maybe their Hong Kong IS can organize a conference for different people?
Good idea.
So any other questions?
Oh, thank you for your talk. You mentioned a lot of ideas in the talk, and some of them maybe also in the paper you published in emergence of functions.
Yeah.
And so when are you going to write to finish this bit out so we can read more clearly?
Yeah, so when we did emergence paper, we were talking about just equilibrium, not a periodic solution. So it's quite a bit similar then. And we talked about emergence, so that in the tissue you would have the same, roughly speaking, the same equilibria with the same local properties would emerge out of a similar reaction diffusion, but it would be in terms of just a same equilibrium, not in terms of a periodic solution. So the periodic solution, I think, is a lot more interesting. It brings us closer to the heart, circadian rhythm, neurology, and a lot of other medical problems too. It's a little more challenging for me. But when we did it originally, we were just working about equilibria and some kind of emergence with equilibria. So in the single tissue, we would have corresponding equilibria being similar in some way for each of the cells in the tissue.
And then maybe about monoticity, like hardwiring it.
No, we have to assume it.
Yes.
That